Hello everyone. This is Akash Deo with the student ID 2023120206. I'm a student of Kongan University in PhD at Department of Electronics Engineering. So today I'm going to make a summary of chapter 3 of book called Introduction to MMIC Technology. So this book talks about MMIC technology and different amplifiers and RFIC. So this is chapter 3, RFIC module design 1, MMIC amplifiers. So this in this whole presentation, the summarize of this chapter 3 will be discussed. The instructor of this course is Professor Namyoung Kim. So moving forward, let's talk about the introduction. So introduction to the basic theory, MMIC amplifiers in wireless communication system will be discussed. Explanation of DC bias injection technique for optimal MMIC amplifier performance. Classical stability and gain analysis method for MMIC amplifiers will be discussed. Overview of various noise types affecting amplifiers performance will be discussed. Practical design examples of MMIC amplifiers, cascade low noise amplifiers, and three-stage power amplifiers will be discussed. Moving forward, we have microwave transistors amplifiers focus on scalability power, DC bias injection sets, operating point for the transistor crucial for its performance and amplifying ACs, various methods of existing applying gates and drain bias voltage, including cut inductor and resistor microstrip stubs, self biasing techniques, and active load, constant current source biasing, and load shifting diodes are among techniques used for efficient amplification. So you can also see the four different circuit designs which explain as a inductor as bias chokes, high value resistor, microstrip stubs, and self biasing. In this, we also have DC bias injection. As we talked in the previous one, so these are two different circuits of the DC bias network E and H, and the stack bias techniques used in three stages of DC biasing. Now, DC biasing also talks about there is a graph curve which explains the typical FET IV curves and operations of DC bias, and the advantage associated with the single power supply are significant, particularly for battery operations, but there is a general penalty caused by the slight increase in DC power consumption. One drawback of the technique is that it removes a useful post fabrication tuning mechanism for the amplifiers because the bias is fixed. Now, classical stability and gain analysis. So this is one of the very important parts. So a diagram of microwave amplifier is given where you can see the voltage source, the resistors, and input matching network, and active device and output matching network is given, and resistance load is also given. According to this, so amplifier stability crucial in design and relies on the uh, S parameter of the active device matching and terminations. Unconditional stability ensures the circuit does not oscillate with any matching network or termination. Stability circles on Smith charts depicts of stability aiding in the graphical amplifier stability stability analysis. The stability parameters mu as simplifies unconditional stability recommendation, replacing us focus complex factors. And these are the few charts of scalability and gain analysis. So which talks about Smith chart illustrating the stable and unstable region in the tau s plane. So you can see this, and another is the condition of unconditionals charts. So this explains this classical scalability and gain analysis. Now we also have a circuit for noise consideration. So there are many noise considerations. One of them is thermal noise. So thermal noise, also known as Johnson and Naismith noise, arises from an random motion of charge carriers in the conductors and leading to in fluctuating voltage. Short noise occurs due to the discrete nature of electric charge, resulting discontinuous pulses of current when charge carriers overcome potential barrier. Flicker noise or pink noise is characterized by functions with IF frequencies dependence over observed in diverse phenomena from cell membrane to transistor noise. And popcorn noise also, there is also called popcorn noise, also called the burst noise of random telegraph signal, and is another type of noise found in semiconductor, which with origin and characteristics that are less understood than other type of noise. And understanding the mitigating various types of noise are essential in designing sensitive communication system, as noise limits uh, system performance and signals fidelity. So you can see the circuit of thermal noise of resistance, where there is a resistance and how this noise is occurred. We also see the noise considerations. What are the noise considerations? So short noise arises from the granular nature of electronics charge occurring when the R is a direct current flow and potential barriers for the charge carriers to overcome. Unlike linear resistors, which don't generate short noises, the discrete nature of charge leads to discontinuous current pulses and electrons hope energy barriers. And short noises randomness in arrival time contributes to its white noises characteristics with the dependence on the electron charge, total DC current and bandwidth. Flickers noise, also known as IF pink noise, is mysterious type of observed in diverse phenomena like cell membrane potential, earth rotation rate, and transistor noise. Another popcorn noise, also termed burst or random telegraph signal (RTS), occurs in inductors and is poorly understood, showing sensitivity and contamination to the IF noises. Let's talk about some practical amplifier design. So you can see a block diagram of a amplifier where there is RF signals, LNA filters, LO mixer, IF, and then the signal is given, which is represented in the right side of the slide. And let's talk in that particular. There is one specific amplifier design called IF design. So in this diagram and where we present a block diagram of KU band LNB, so LNA and LNB. So let's talk about the KU band LNB down converts satellite frequencies to set up box compatible signals featuring major performance parameter like linearity, noise removals, and frequency conversions. Indium gallium phosphate SBT technologies with characteristic like high linearity of optimized fabrication process is utilized for the design, ensuring efficient operations within the specific parameter. A two-stage broadband IF amplifier is designed to achieve flat gain over the desired bandwidth, utilizing common emitter configuration and voltage divider bias for stabilization. Lossy matching techniques are employed with the amplifiers matching network to ensure flat gain responses over the broadband. Fabrication and measurement involve on-chip testing using CPW configuration and water proofs with results showing efficient power consumption, high gain, and desired frequency responses. So here are a few examples of IF amplifier designs. So you can see the images. So first is a simplified schematic of the amplifiers where input matching, intersect matching, and output is given. Another is lossy matching, which have no connections between input matching, intersect matching, and output matching. And there is another layout of MMIC IF amplifiers, which is 1000 into 1200 micrometer square, which is a very small and micro scale MMIC IF amplifiers used in MEMS, and which is being designed by Professor Namyoung Kim in Kwangwon University. Let's talk about indium gallium phosphate HBT characteristics. So utilizes HBT devices parameters beta equals to 115, FT equals to 15 GHz, and Fmax equals to 80 GHz with breakdown voltage of VVCO is equals to 13.8 volt, BVCO CBO equals to 26.5 volt and BVEBO equals to 7.4 volt. Implements a 6-inch INGP SBT technology with 4 emitters fingers. Device features emitters with 2 micrometer length, 20 micrometer, base with 1 micrometer, collector width 8 micrometer. Operates at the 50 milliampere typical current consumption with the maximum of 60 milliampere and junction temperature of 150 degrees Celsius, optimized for MMIC capacitor, spiral inductor, NICR in the film resistor via holes and transmission lines. Now one of the design which previously discussed as a cascade LNA design is been discussed in this slide, and with the diagram, block diagram, Ku band LNB as a super hydronite font in. So this is a particular design, circuit design of LNB or as a super hydronite font in. So the Ku band LNB functions as a super heterodyne font in converting satellite frequency for the set-top box compatibility. Utilizing indium gallium phosphate and gallium arsenide SBT technology as a cascade LNA is designed with the specific emitter characteristics and optimized biasing for low power consumption and minimized noise. The cascade stage incorporates a series of resonator for tunable image rejection control through Q tuning and voltage adjustments. Fabrication involves the die attachment of the substrate and after level probe testing, resulting a compact LNA with the satisfactory gain and image rejections. Now measurements results demonstrable pass band figure images reactions and 1 dB gain compatibility, summarizing the cascade LNA's performances. Now let's see the figure of a schematic diagram of a cascade LNA with the image reject node. So this is very complex, where there is also tunable image reject nodes is represented, and a junction capacitance various function as a BC junction diode at which is been calculated at the Hong University is also presented. Now let's talk about power amplifier designs. So here a sample for configuration of 3-stage power amplifier is there, like stage 1 input matching, and stage 2 is inter-stage matching, and stage 3 is inter-stage matching again, and then output matching is given. And another circuit is a complex stage 1, stage 2 and stage 3. Whole circuit design is represented with different resistor and capacitors. So a power amplifier PA is crucial for increasing the power level of signals, impacting output power small signals gain. The presented 1 watt power amplifier CDMA employs the gallium phosphate and gallium arsenide SBT technology in 3-stage configuration. Utilize the vertical bipolar intercompany VVIC model to extract accurate large signals characteristics of the indium gallium phosphate and gallium arsenide SBT. The design process considers efficiency, power matching, and the load pull method for optimal performances. Now, fabrication and results sought scalability and power output suitable for the cascade design. And these are for few examples, more examples of the power amplifier designs. Energetic schematic representation of power amplifier operations, which is given by this particular image, where it represents RF input power pin, DC power PDC, and RF output power. And the comparison characteristics of intense solid curve and power matched dotted curve is given in the right side figure. The main important factor of this RF is like how to fabricate and do measurements. So these are few parameters. So parameters is frequency gain, input return, loss output return, and flatness, and P1 dB. So the units of frequency is gigahertz, gain is dB, input return is dB, output return is dB, and F1 dB is dBm. So requirement for frequency is 0.95 to 2 gigahertz. Gain is almost greater or equal to 30 dB. Input return greater than less than 15. output return less than 15, flatness almost equal to 1.5, and dBm 3.5 dBm. Simulations compatibility should be 0.95 to 2, and gain should be 30.6 or maximum 31.6, and input return is 22 to 17, or output is 12 or 16, flatness 1, and P1 dB should be 3. Now measurement parameters is almost equals to the requirements, like frequency 0.95 to 2 gigahertz. Gains would be 26.2 to 27.6. Maximum it can be up to 27.7. Now input return loss is 24 or 2320. Output return 12 or 9. Flatness almost equal to 1.5, and PD1 should be not more than 3. So these are the things. Thank you very much. So this is the overall summary of chapter 3. Thank you.